We shall now take up the essence of what locality-sensitive hashing is all about by defining an abstract notion of an LSH family of hash functions. Using this abstract definition, we show how to build new families out of old families in such a way that the new family has a steeper S-curve than the original family. The construction we use are quite analogous to the way we worked with min-hash functions, which are an example of an LSH family, and use the combination into bands to steepen the S-curve. Before proceeding, we need to explain something about what a hash function in the sense of an LSH family really is. Technically, a hash function h in this sense takes two arguments, x and y, which are elements whose similarity or distance we are interested in. The hash function returns a decision about this pair. Yes means that they are a candidate pair and we need to calculate their similarity. We can think of yes as saying x and y belong to the same bucket when a hash function h is used. But the answer no means that x and y is not a candidate pair according to this hash function. For example, a min-hash function can be viewed as taking two sets x and y, computing their min-hash values according to some permutation associated with that hash function, and saying yes if and only if the min-hash values are the same. In many cases, there will be a calculation of values behind the scenes, and the yes answers are made when the values are the same. However, the view we are taking now is more general, since there need not be a computation of values that are then compared. And as we shall see, we really need this generality. For example, we should look at LSH families that render their decisions by looking at many values and saying yes if there is at least one equality. However, to make things look more normal, we shall often use the expression h of x equals h of y to mean that h of x and y is yes. Okay, so here's the definition of an LSH family of hash functions. First, these families of hash functions each assume that the data consists of a space of points with a distance measure for that space. For example, the family of min-hash functions assumes the space of points as sets, and the distance is the Jacquard distance. There is no notion of a family of hash functions being sensitive in some absolute sense, but rather we can make statements about a family H of hash functions in terms of four parameters. There are two distances, d1 and d2, and there are two probabilities, p1 and p2. Of the two distances, one is a small distance, that's d1, and the other is a large distance. The probability p1 is associated with the small distance, and it is a lower bound on the probability of agreement for points at distance d1 or less. The second probability, p2, is associated with the large distance, and it is an upper bound on the probability of agreement for points at distance d2 or more. We expect p1 to be large and p2 to be small. Okay. More formally, for any 2 points x and y at distance up to d1, the probability considering all hash functions little h in the family capital H, that little h says yes about x and y, is at least p1. And if the distance between x and y is at least d2, then the probability that little h says yes for x and y is at most p2. Here's a picture of what we know about the probability of h of x equaling h of y. For distances d1 and below, we know the probability is at least p1, and for distances d2 and above, we know the probability is at most p2. Between d1 and d2, we know nothing. However, we shall try to make the difference between d1 and d2 very small, and the distance between p1 and p2 as large as we can. Okay, that will give us the S-curve we want, although since we are now talking about distances rather than similarities, the S-curve is backwards. It drops down precipitously between the distances d1 and d2 rather than rising precipitously. So it looks something like this. Let's take as our example the only example we know. The underlying space consists of sets, all subsets of some universal set, and the distance measure is Jacquard distance. The LSH family is the family of min-hash functions, each based on one of the possible permutations of the members of the universal set of elements. We claim the probability that a given min-hash function h gives the same value for sets x and y is 1 minus the Jacquard distance from x to y. That's just a restatement of the theorem about how the Jacquard similarity is the probability that two sets agree on a random min-hash function. Notice that 1 minus the Jacquard distance is the Jacquard similarity. We claim that the family of min-hash functions is a 1/3, 2/3, 2/3, 1/3 sensitive family for the space S of sets and the Jacquard distance d. For example, the first and third parameters say that if the distance is at most 1/3, then the probability of agreement is at least 2/3. But that makes sense because if the distance is at most 1/3, then the Jacquard similarity is at least 2/3. And we know that the probability of agreement equals the similarity. Likewise, the second and fourth parameters say that whenever the Jacquard distance is at least 2/3, so that the similarity is at most 1/3, the probability of agreement is at most 1/3. We can make many statements like this about the family of min-hash functions. There's nothing special about 1/3 and 2/3. In fact, for any distances d1 and d2, as long as d1 is less than d2, the min-hash functions form a family with sensitivity d1, d2, 1 minus d1, 1 minus d2. When we start with a simple LSH family, such as the set of min-hash functions, we don't get the S-curve effect. However, we're going to see that it is possible to amplify the steepness of the S-curve using two constructions that produce a new LSH family from a given LSH family. These constructions are like what we've already seen for the min-hash functions. In particular, what we call the AND construction is essentially the combination of the effect of several rows in one band. And the OR construction is the combination of several bands. So here is the AND construction. We're given an LSH family H, and we want to construct from it a new family H'. Each hash function from H' is built from R functions from H. A hash function little h in the family H' is constructed from a set of R hash functions from family H, say H1 through HR. Little h renders its decision about a pair of elements x and y by checking that each hash function in the set renders the decision yes. Using our convention that h of x equals h of y means that the answer for x and y is yes, we can write the rule for h as shown. That is, h of x equals h of y if and only if hi of x equals hi of y for all I, where I ranges now from 1 to r. The family H' amplifies the effect of H according to the rule given here. The lower and upper distances d1 and d2 don't change. However, the two probabilities are each raised to the rth power. That is, in order to get a yes from hash function h, we have to get yes from each of the hi's. The family H' consists of all possible sets of R members of family H, so the hi's for a given h can be viewed as randomly chosen and thus independent. Remember that the rule for the probability of independent events occurring simultaneously is the product of the probabilities of the individual events. The AND construction corresponds to combining rows in a band. We also have an OR construction that corresponds to combining bands. Again, we'll start with an LSH family H and construct a new family H'. Each member of H' will be constructed from a set of B functions from H. Let little h be a typical member of the family H', and let x and y be elements to which we want to apply little h. Then we say h of x equals h of y if and only if hi of x equals hi of y for at least one value of I in the range 1 to b. Okay. Notice that the expression h of x equals h of y really is shorthand for the way h looks at both x and y and decides whether or not to make them a candidate pair. We cannot explain what is going on by supposing that h computes a value from x and a value from y and simply asks if they are equal. So here's the rule for the sensitivity of family H prime in terms of the sensitivity of H. As for the AND construction, the distance components D1 and D2 do not change. But the probabilities are altered according to the rule for the probability of the OR of independent events. Okay. To see how this combination works, think of at least one of these events occurs. In its equivalent form, it is not true that none of these events occurs. If each event occurs with probability P1, then the probability it doesn't occur is 1 minus P1. The probability that none of B events occurs is that raised to the bth power. And 1 minus that is the probability that none of them occur is false. That is, at least one of the B events occurs. The same transformation applies to the other probability P2, of course. So here's a summary of what happens when we apply the AND and OR constructions. AND makes both the high and low probabilities shrink because we're taking two probabilities which are less than 1 and raising them to the rth power. What we need to do is pick R big enough so that the low probability becomes close to 0, yet pick R small enough that the high probability stays significantly above 0. It's a balancing act, but we'll see in a moment how it works in practice. The analogous story applies to the OR construction. Both probabilities grow, but we contrive to select a value of B that makes the high probability get very close to 1 while still keeping the low probability significantly away from 1. Now we need to see how to compose the AND and OR constructions in order to wind up with an LSH family where the low probability is essentially 0 and the high probability is essentially 1. That's the ideal for the S-curve, remember. In the case of signature matrices and the band construction, we did the AND construction combining rows in a band, followed by the OR construction combining bands. But we could actually have done these in the reverse order, and it is also possible to use a sequence of more than 2 of the AND and OR constructions alternating, and we'll see how to do that, how that works in a moment. But suppose we do the R-way AND construction followed by the B-way OR construction. The AND construction turns a probability P into P to the R. Then the OR construction turns P to the R into this function. Notice that what we have is exactly the S-curve that we constructed when we originally discussed LSH for min-hash functions. We're going to do an example on the next slide where R and B are both 4. That is, starting with some LSH family H, we do a 4-way AND construction to get a family H prime, and then use H prime to do a 4-way OR construction to get a new family H double prime. So here's a table of what happens to the probability P when you apply the 4-way AND followed by the 4-way OR. We can pick the lower and upper distances D1 and D2 as we like. For example, here's what happens if we choose the lower distance D1 to be 0.2 and the upper distance D2 to be 0.8, and the underlying LSH family is the min-hash functions. We start with a 0.2, 0.8, 0.8, 0.2 family. The constructed family has the same distances 0.2 and 0.8. But if you substitute P equals 0.8 in this formula, well, you get this. You get 0.8785. So the upper probability is raised. That's good. And if you substitute P equals 0.2 in the same formula, you get 0.0064. So the lower probability is lowered. That's also good. We also have the option of starting with a B-way OR construction and then doing an R-way AND construction. The OR construction turns any probability P into this expression, and then the AND construction raises those probabilities to the rth power, giving this formula. The S-curve you get from this sequence of constructions is related to what you get if you start with the R-way and then do the B-way or. Starting with that curve, you mirror it vertically and then mirror it horizontally, or mirror it first horizontally, then vertically. It doesn't matter. The result will be the curve for this expression. We'll again do an example on the next slide. It is a four-way OR followed by a four-way AND. So here's the table for the OR AND construction, each using 4 from the previous LSH family. Let's see what you get when you start with the min-hash functions, thought of as a 0.2, 0.8, 0.8, 0.2 sensitive family. Looking up the values for probabilities 0.8 and 0.2 in the table, you see you get a much higher probability for the low distance pairs, that's this, and you also get a somewhat lower probability for the distant pairs. And so again, both have been improved. We are free to apply construction after construction, and if we pick the right values of R and B, we'll keep improving both probabilities, driving the low one toward 0 and the high one toward 1. For example, we could apply the OR followed by AND construction we just discussed, and then apply the AND followed by OR construction discussed earlier. That, by the way, would be the same as applying a 4-way OR, then a 16-way AND, and finally another 4-way OR. Notice that each construction uses 16 of the original functions, so by cascading these two constructions, we use 256 min-hash functions. If you do the math, you'll find that it transforms the min-hash functions, thought of as a 0.2, 0.8, 0.8, 0.2 sensitive family, into this. The probability of saying yes for sets at Jacquard distance 0.2 or less is this, which is almost precisely 1. That is, there are very, very few false negatives. But the probability of saying yes for sets at Jacquard distance 0.8 or more is this very small probability. Thus, at least among pairs that are really far apart, the number of false positives is tiny. You might look at this analysis and observe that we don't know anything about what happens for similarities between 0.2 and 0.8, and that's a big range. However, suppose our application is shingled web documents. If we take 2 random web pages and we've used a large enough shingle length, say 9 or 10, then 2 random documents will have a very small Jacquard similarity, and thus a Jacquard distance above 0.8. Only if there is some special cause for similarity, say a mirror page or plagiarism, will the Jacquard distance be low. And in those cases, we expect it to be very low, probably under 0.2. That is to say, there simply aren't many pairs at distance between 0.2 and 8 in this application. The conclusion is that for the particular application, we might be happy with distances 0.2 and 0.8. But we are free to make the distances be whatever we want, as long as the first is less than the second. For example, we could start with a 0.49, 0.51, 0.51, 0.49 sensitive family, and do constructions that would drive the probabilities, which are initially 0.51 and 0.49, close to 1 and 0, respectively. Of course, we would need many more than 256 of the base functions to get such a steep S-curve. What I'd like to do now is explain how to select the values of R and B for AND and OR constructions. Let's look at the function that we've called the S-curve. That's this. This is a function of the probability P, and it has 2 parameters R and B. An interesting observation is that this curve, okay, let's draw something like that here. It has a fixed point t, such that if p equals t, then the result of applying the function to t is t itself. To see that t exists, look at where the curve intersects the line with slope 1. Okay. So that would be the value of t. Above probability t, applying the S-curve function increases the probability, while below t, the probability decreases. We can conclude that as long as the two probabilities are on opposite sides of t, the construction where you do an R-way AND followed by a B-way OR will move both probabilities in the direction we want them to go. We can then iterate this construction as many times as we like, and both probabilities will keep improving. There's an analogous observation about a construction where we do an OR followed by an AND. The S-curve formula is a little different, but the ideas are quite the same. Here's a picture suggesting what happens for the S-curves that we get for both the AND and OR-AND constructions. The threshold is defined by the place where the S-curve and the straight line cross. Okay. For probabilities p below t, applying the S-curve function lowers the probability. While for probabilities above t, the S-curve sends p to a higher probability.